Okay, so today we will start with chapter 1, which is on crystal structure. Before I start talking about the crystal structure, we need first to learn how to describe materials in 3 dimensions. At this point, it's worth remembering from last lecture that by learning more about atomic scale properties of materials, how they bond, how atoms are arranged, we can learn more about macroscopic properties of these materials, such as their hardness, elasticity, superconductivity, ferromagnetism, and hence we can build up new materials with specific properties to study. Crystalline solids. This is one type of solid state physics we are going to study, crystalline solids. It's some sort of periodic arrangement of atoms, and very frequently the macroscopic morphology is determined by its underlying structure. For example, let's look at this image. This is quartz silicon dioxide. It's a beautiful crystal, and we can see that its structure is somehow reflecting how the atoms are arranged. Quartz silicon dioxide has a different form, amorphous material. In this image, the blue objects represent silicon and the red dots represent oxygen. Each silicon is bonded to 4 oxygen atoms, and each oxygen is bonded to 2 silicon atoms. We are familiar with this material as window glass. It has lots of shared properties with its crystalline counterpart, but it's a slightly different material. Now I will start by giving some important definitions that will help us learn more about the topic. So we will start with a crystal. So a crystal is a periodic arrangement of atoms. For example, we can see these 3 different crystals over here. We can see a simple crystal on the left, and more complicated crystals on the right. They can have many different types of atoms in complicated arrangements, but as long as they are periodic, then it is a crystal. A lattice. There are 3 different definitions for a lattice. We will start with definition A. It's a set of points defined as integer sums of primitive lattice vectors. In 1 dimension, if I take these points over here, in order to reach any point, so let's take this point, for example, as the center. Okay, in order to reach any point, for example, to reach this point, R, that is this point, is 1 times this distance A. In order to reach this point here, so this point R is 2 times this A. So we represent any point as R equal N, where N is an integer, so N belongs to that. And A is what I mean by primitive lattice vector. Okay. Now, in 2 dimensions, this R will be N1 times vector A1 plus N2 times vector A2, where the A's are primitive lattice vectors. We will refer to them by PLVs from now on. They are non-collinear. Non-collinear, I mean A1 and A2 will not be along the same line, because if they are along the same line, I will not be able to reach other points in the lattice, okay? And the N's are integers. The N's are integers. Okay, let's focus here on this lattice, and let's assume that this point over here is the center. Okay, let's take this point over here as the center. If we take A1 and A2 to be the primitive lattice vectors, then to reach any point, let's say we want to reach this point over here. To reach this point over here, we have to go 2 times A1 plus 1 times A2. Okay, so it is 2 times A1 plus 1 times A2, or we can refer to this point as 2, 1. Okay, so if we think of this lattice point here again, so if we think of this lattice point here as the center, as point 0, every point in this lattice, is an integer times A1 plus an integer times A2. So for example, again, if I want to come to this point over here, let's say I want to come to this point over here. Okay, so how do we go there? We go 2 minus 2A1 plus 2A2. Okay, any point in the lattice can be reached as integer times the first lattice vector, primitive lattice vector, plus integer times the second primitive lattice vector. Okay. Now, in 3 dimensions, it is very similar, but the drawing will become more complicated, so we can just imagine it. To reach any point R in space, it will be N1 times A1 plus N2 times A2 plus N3 times A3, where the A's are not coplanar. That is, I can cover the whole space, and R can be represented as N1, N2, N3, similar to how we represented it in 2 dimensions. One thing we need to be aware of, is that the choice of primitive lattice vectors is not unique. Okay, so for example, for this lattice over here, we can choose these 2 to be the primitive lattice vectors, these 2 to be the primitive lattice vectors, these two, or these 2. Okay, so it's not unique. Any one of these, any set of these will be perfectly okay. The important thing is that any point on the lattice should be expressible as an integer sum of the PLV. So that's the important thing. That is, if I pick any point, I can represent it in terms of the integer sum of these 2 vectors. So for example, to reach here, I have to go from here to here, then from here to here. So this is really PLV. Now let's look here. Let's look at this lattice. Are these PLVs? Okay, so they are PLVs if I can reach any point as integer sum of these 2 vectors. Is it possible? Yes, it is possible by just any combination of these 2 vectors. I can cover all the points on the lattice. So these 2 are PLVs. Let's take another example. For another lattice, are these 2 PLVs? In this case, it turns out it's not, because if I take the combination of them, there will be points missing out. So this combination, these 2 PLVs are, these 2 vectors are not primitive lattice vectors for this lattice. What are other definitions for a lattice? So definition B, it's a set of vectors such that addition of 2 gives a third. In simple terms, if I take here, for example, let's do it in a different color. Okay, if I take this vector plus this vector, what does it give? It gives this vector, which reaches a third point on the lattice. Okay, so if I take the addition of 2 points on the lattice, it gives a third point. Okay, definition C. Lattice looks exactly the same when viewed from any lattice point. So for example, let's take this point over here. let's take this point over here, okay? Let's look at its environment. So there is one point on its right, a certain distance, one point on its left, a certain distance, one point down, a certain distance, making a certain angle, one point in this direction, one point in this direction, okay? If I take any other point, let's say I take this point over here, okay? I will see that there is this point on the right, a certain distance, exactly the same distance as this. There is this point to its left, exactly the same distance as this one. There is one point down, exactly the same distance as this one. There is one point here, exactly the same distance and making the same angle as this one. Okay, so we will notice that there is every point has exactly the same environment around it. Let's look at this structure over here, and let's see if it is a lattice. Okay. In particular, let's look at the 2 points R and P. We will see that R has these 2 points, whereas P doesn't have these 2 points. Okay. And an easier way to see it is R has point P downward, whereas P has point R upward. So it doesn't have a point downward similar to R. So point R and P are not equivalent. P and Q, however, are equivalent. But just because R and P are not equivalent, then this is not a lattice. Okay. So this is a third way to see if the structure is a lattice or not. So what is the first definition? Let's go back to the first definition. It's a set of points defined as integer sums of primitive lattice vectors. That is, if every point on the in the structure can be represented as integer sum of primitive lattice vectors. This is not always easy to see. Okay, this is not always easy to see, and this is why we have 2 other definitions. One definition which says that it's a set of vectors such as the addition of 2 gives a third. Okay, so if I take 2 vectors and add them, I get a third one, which reaches a point on the which a lattice point. Okay, and the lattice looks exactly the same when viewed from any lattice point. Okay. Any periodic structure is a lattice. Any periodic structure is a lattice of repeating motifs. Any periodic structure is a lattice of repeating motifs. Look at this periodic structure of flowers. Okay, this periodic structure of flowers, we can see it as lattice points, where every lattice point is covered by a flower. Okay, so if we take this lattice over here and replace each point on it with a flower, we get the whole periodic structure drawn as lattice times, we represent it as lattice times the repeating structure, which is in this case a flower. Another example, this is certainly a periodic structure, which we have this triangular lattice, okay? And if on each lattice point we put this mouse, then we get this periodic structure, okay? This is also a periodic structure. This is a cubic lattice times, this is a cubic lattice times this repeating object. It gives us this periodic structure. A new definition now, a unit cell. A unit cell is a region of space which, when repeated and stacked together, reconstructs the full periodic structure. So let's look at this periodic structure over here. Okay, let's look at this periodic structure over here. What I'm showing you here in green is a unit cell, because if I put the unit cell over here, okay, if I put it on top of the whole structure and I can stack them together, then I can cover the whole structure. So what we see here is a unit cell, okay? So it's a region of space which when repeated and stacked together, that is if I put one here, one here, one here, one here, one here, it will reconstruct the full periodic structure. There will be no space between them, okay? There will be no space between them. This is exactly like the tiles in a bathroom, okay? The tiles will reconstruct the whole space. Another one is this mouse over here. We have a unit cell which contains one mouse. We can stack them all together. See, we can stack them all together to reconstruct the whole periodic structure. Okay. What is important about unit cells is that we can stack them together with no space between them. So again, this is like the bathroom tiles. So this is a unit cell. This is here another example of a unit cell. So this is here the previous example that we said it is not a lattice, but it is definitely a periodic structure with this repeating unit. This is the repeating unit. So if we look at this unit cell and we stack them next to each other, we can rebuild all of this periodic structure. Another important definition is a primitive unit cell. A primitive unit cell is a unit cell. So it is one of these cells that reconstruct the whole periodic structure, but it has exactly one lattice point. So examples here, there is only one lattice point because these mice are on top of these lattice points, okay? Here also in green, there is only one lattice point. You will see it in red. And here also in green, this is the unit cell, and there is only one lattice point inside it. So all these are primitive unit cells. Primitive unit cell is not unique. So for the same periodic structure, look at this, all these four represent the same periodic structure, but we can have different primitive unit cells. So we can take them this shape, this shape, this shape, this shape. Okay. As long as they fit together and that the tile the whole space, then we have different primitive unit cells. Some of them might be more convenient than others. Definitely, this is more convenient than this, for example. Okay, another definition. Okay, before the new definition, for this periodic structure, this is one primitive unit cell. So this is a primitive unit cell that it's definitely a unit cell, because if I draw another one and another one and another one and another one, it covers the whole periodic structure, and it contains only one lattice point. So it is a primitive unit cell. Another example is this. This is also a unit cell, because if I draw another one here and another one here and another one here and another one here, I can stack the whole space. And in this case, we also have one lattice point, but it's broken into two pieces. So here it's very important to see that this unit cell contains half of this and half of this. So this is one lattice point. So this is also a primitive unit cell. Very good primitive unit cell also is this one. Okay, so this is also a unit cell because I can stack the whole space by it. So if I put this one, this one, this one, this one, I can cover the whole space. So it is a unit cell. And it's primitive because it has one lattice point, which is broken into 4 pieces. So here I have 1/4 of this, 1/4 of this, 1/4 of this, 1/4 of this. So it contains exactly 1 lattice point. Conventional unit cell. It's a non-primitive unit cell. So it is not a primitive unit cell. That is, it contains more than 1 lattice point. But it is convenient. Why would it be convenient? Because usually meaning orthogonal axes. If we look at this periodic structure, we notice that the unit cell is triangular, okay? But the triangular unit cells are not conventional. So usually conventional ones are orthogonal ones. So here, instead of taking this triangular unit cells, we take this rectangular unit cell, and it is not primitive because it contains 1 lattice point and another one, which is the combined sum of these quarters over here. Okay, let's move forward. Another important cell is the Wigner sites cell. It's the region around a lattice point closer to that lattice point than to any other. You have all bunch of lattice points. So for any periodic structure, you have all bunch of lattice points. You would like to find the region around 1 lattice point. So let's take this point here, the black one. We want to find the region around this point that is closer to it than to any other lattice point, okay? And that's what when we find this region, this is what we call a Wigner sites cell. How do we find this region? There is a way to do it, and I will show you how to do it. It's easier to show than to describe, than to write it down. We construct it using perpendicular bisectors. So what we do is the following. So here is a lattice, and the black point is the point I'm interested in, the one that I would like to draw the Wigner sites cell around it, okay? So I start by taking 1 point close to it. So let's assume I take this point number 1. I draw the perpendicular bisector. Then I draw the perpendicular bisector, the red line. Everything on the lower side, everything here on the lower side is closer to the black point than it is to the blue point. This is the perpendicular bisector. So everything here is closer to this blue point over here. We do the same with another point. So we take point 2 and we do the same. We draw the perpendicular bisector. And now we know that everything on the right of the red line is closer to the black point than it is to the blue point. I do the same thing with point 3, with point 4, with point 5, and with point 6. Okay? And now what I have, and now what I have is this region. I labeled it here in green. Now we have this nice region, which is called a Wigner site cell, and it happens to be a primitive cell. Why is it a primitive cell? Because it contains exactly 1 lattice point, and it can tile the whole periodic structure. Okay, I can stack these Wigner site cells next to each other, and I can reconstruct the whole lattice. Okay, so it is a nice primitive unit cell. This is in 2 dimensions. In 3 dimensions, it looks something like this. Oh, the last idea for today's lecture, it's the idea of a basis. So Basis is a description of objects in unit cell with respect to a reference lattice point. What do I mean by that? Let's look at this crystal. This crystal is made up of two different atoms. There are these large light atoms, and there are these small dark atoms, okay? And the dots are just reference lattice points. So the dots are not atoms, they are just reference lattice points. So let's take this unit cell, for example, okay? It's blown up over here. So here you can see a bigger image of this square over here, okay? So what do we have? We have the basis for the basis. We should list off all of the objects in the unit cell reference to the reference lattice point called 0, 0. So we take this reference point to be 0, 0, and we have to say what is inside this unit cell with respect to this 0, 0. And this is our basis, okay? So we will say, for example, there is a large, so we will say for the basis, we have a large light gray atom at position what? Okay, at position A is from here to here. So from here to here is A. So this is at position A over 2, A over 2, okay? And we have small dark gray atoms at position A over 4, A over 4, 3A over 4, A over 4, 3A over 4, 3A over 4, and A over 4, 3A over 4. Once I've given you all of this list, once I have given you all of this list of where are all of these objects in the unit cell with respect to the reference point, I have given you a basis for the crystal. So if I tell you the lattice, if I tell you the lattice is triangular or rectangular or whatever. So if I tell you what is the lattice and I tell you the basis, this means I told you the whole crystal. So this is the language we need in order to describe the whole crystal. Okay, so today we covered lots of important definitions. Next, in the next lecture, we will start immediately by looking at three-dimensional crystals, and in particular, we will focus on cubic crystals. So that's it for today. Bye-bye.